Close your eyes for a moment and imagine this. A spacecraft leaves Earth carrying the greatest minds humanity has ever produced. Its engines burn brighter than these. Nations celebrate. Billions watch the sky as humanity begins its first journey to another star. It feels like the beginning of a new age, the moment human beings finally escape the limits of one tiny planet. But now imagine something terrifying. What if the universe never intended us to reach the stars? What if the problem is not our technology, but reality itself? Tonight, we are going to confront one of the most uncomfortable ideas in all of physics. That interstellar travel may not just be difficult, it may be fundamentally impossible. Not because humans are weak, not because scientists lack imagination, but because the laws of the universe are brutally strict. We grow up believing science removes limits. We are told that every generation breaks barriers the previous generation thought were impossible. Humans crossed oceans, conquered the skies, walked on the moon, split the atom, and touched the edge of the solar system with robotic explorers. So naturally, we assume the stars are next, but space has a secret. The universe is not empty. It is not friendly, and it is not built on human intuition. The deeper physicists looked into space, time, energy, and motion. The stranger reality became. Distance stopped behaving the way we expected. Time itself began to bend. Energy requirements exploded beyond imagination. Even light, the fastest thing in existence, suddenly seemed painfully slow. And hidden inside these discoveries is a chilling possibility. The stars you see every night may forever remain out of reach. In this journey, we are going to explore why the speed of light acts like a cosmic prison, how time itself breaks apart near extreme speeds, why a single grain of dust could destroy a spacecraft, and why the human body may be completely unsuited for deep space travel. But more importantly, we are going to uncover something far deeper than rockets or engines. We are going to discover what the universe is truly telling us about our place inside it. Because sometimes the most fascinating scientific discoveries are not the ones that give humanity more power, but the ones that reveal where the limits actually are. And once you understand these limits, you will never look at the night sky the same way again. People often imagine interstellar travel as if it is simply the next step after airplanes, rockets, and moon landings. We think that because humanity crossed oceans, climbed mountains, and stepped onto another world, the stars must eventually become reachable too. But physics does not care about human ambition. The universe is not designed around our dreams. It follows laws, and those laws are incredibly strict. The deeper scientists looked into reality, the more terrifying they realized the challenge truly is. Interstellar travel is not just difficult because our technology is weak. It may be difficult because the universe itself is built in a way that resists it. The first great barrier is the speed of light. Light moves at about 300,000 kilometers every second. That number sounds enormous because it is enormous. In 1 second, light can circle Earth more than 7 times. To the human mind, that feels almost magical. Yet even at that unimaginable speed, light still takes over 4 years to reach the nearest star beyond our sun. That means if the sun suddenly vanished, Earth would continue orbiting peacefully for 8 minutes before we even noticed anything had changed. Space is so vast that even light struggles against it. According to Einstein's relativity, nothing with mass can reach or exceed the speed of light. This is not a technological limitation like a weak engine or poor fuel efficiency. It is woven into the structure of space-time itself. As an object moves faster, its mass effectively increases, and the amount of energy required to accelerate it rises dramatically. Near the speed of light, the required energy becomes absurdly large. EMC2, that famous equation, is not just about atomic bombs. It tells us mass and energy are deeply connected. To push a spacecraft carrying humans anywhere close to light speed would require amounts of energy comparable to what entire civilizations produce over vast periods of time. And then comes the cruel twist. After spending all that energy accelerating, you must somehow slow down when you arrive. Otherwise, your glorious interstellar mission becomes a cosmic bullet screaming helplessly through space forever. People often say, why not just keep accelerating? But acceleration itself becomes deadly. The human body is fragile. Even fighter pilots black out under extreme forces. A spacecraft constantly accelerating for years would need engineering perfection beyond anything humanity has ever achieved. Tiny failures become catastrophic at relativistic speeds. Then there is time dilation, one of the strangest consequences of relativity. Time itself changes depending on motion. If astronauts traveled near light speed, time for them would slow down relative to people on Earth. A crew might experience only a few years passing during their journey, while decades or centuries pass back home. Imagine leaving Earth to explore another star and returning to discover everyone you ever knew is dead, entire nations gone, languages transformed, history erased. Interstellar travel does not merely separate people by distance. It separates them through time, delta t, 1v2, SLE2. That equation represents time dilation. And hidden inside it is a horrifying truth. The faster you move, the more disconnected you become from the rest of humanity. Science fiction often treats this like an interesting side effect, but emotionally it would be devastating. Astronauts would become temporal refugees. Even successful missions could destroy the human meaning of coming home. Another misconception is that space is mostly empty, so traveling through it should be easy. But empty does not mean harmless. Interstellar space contains particles, atoms, radiation, and dust. At ordinary speeds, these are insignificant. But near light speed, even microscopic particles become lethal. Imagine a grain of sand striking a spacecraft traveling at relativistic velocity. The impact energy would resemble an explosion. Tiny particles, invisible to the eye, could rip through metal like bullets through paper. Radiation becomes another nightmare. Cosmic rays move through the universe carrying tremendous energy. Earth's magnetic field shields us from much of this invisible bombardment, but deep space offers no such protection. A spacecraft traveling for decades or centuries would face continuous exposure to radiation capable of damaging electronics, mutating DNA, and causing cancer. To shield against it, the ship would need massive protective layers, but more shielding means more mass, and more mass means even more energy needed for acceleration. Every solution creates another problem. Physics behaves almost like a locked door with endless locks behind it, and then there is the sheer scale of distance itself. Humans evolved in a tiny corner of one planet. Our brains are not equipped to emotionally grasp cosmic scales. Numbers stop feeling real. The moon seems far away until you realize every planet in the solar system could fit between Earth and the moon with room left over. The nearest star system, Alpha Centauri, is about 40 trillion kilometers away, DVT. This simple relation between distance, velocity, and time becomes terrifying in space travel. Suppose you travel at the speed of the fastest spacecraft humans have ever built. Reaching the nearest star would still take tens of thousands of years. Entire civilizations would rise and collapse before the spacecraft even arrived. People sometimes imagine giant generation ships where multiple human generations live and die during the voyage. But such missions introduce completely new problems. Human societies are unstable even on Earth, where food, sunlight, gravity, and ecosystems exist naturally. Now imagine a tiny isolated population trapped inside a metal cylinder for centuries. Political conflict, psychological collapse, resource shortages, and social decay become enormous threats. Humans are biological creatures shaped by Earth's environment. We are not designed for deep space. Astronauts aboard the International Space Station already suffer muscle loss, bone density reduction, vision problems, and immune system changes after relatively short missions. Now imagine decades or lifetimes in microgravity. The human body begins to fail because gravity is not merely something we experience. It is something we evolved with. The mind suffers too. Isolation affects psychology in profound ways. On Earth, humans can look at oceans, trees, clouds, cities, and faces. In deep space, there is darkness and machinery. Day and night lose meaning. Silence becomes oppressive. A journey lasting generations could create unimaginable mental strain. Even communication breaks down across interstellar distances. Signals moving at light speed still require years to travel. Conversations become impossible. Imagine sending a message to Earth and receiving the reply a decade later. Interstellar explorers would exist in total isolation from human civilization. And then comes the fuel problem, perhaps the most brutal engineering nightmare of all. Rockets work by throwing mass backward to move forward. The more fuel you carry, the heavier the spacecraft becomes. But heavier spacecraft require even more fuel. This creates what engineers call the tyranny of the rocket equation, delta V, VV. This equation governs rocket motion, and it reveals an ugly truth. To achieve higher speeds, rockets require exponentially larger amounts of fuel, not slightly larger, exponentially larger. A spacecraft capable of interstellar travel using conventional rockets would need absurd fuel masses, perhaps larger than mountains or even planets. The universe demands a terrible price for speed. Some people propose nuclear propulsion, antimatter engines, or warp drives. These ideas are fascinating, but they do not magically erase physical laws. Antimatter contains enormous energy, yet producing even tiny amounts is extraordinarily expensive and dangerous. Warp drives sound exciting because they supposedly bend space-time itself, but calculations suggest they may require exotic forms of matter with properties never observed in nature. Wormholes offer another science fiction dream: shortcuts through space-time. But theoretical wormholes appear unstable. They might collapse instantly or require negative energy densities beyond anything known to exist naturally. Physics does not forbid human imagination, but imagination alone cannot overpower equations. There is also thermodynamics, one of the most merciless areas of physics. Every machine generates waste heat. In space, removing heat becomes difficult because there is no air to carry it away. Spacecraft traveling with enormous power systems would face dangerous overheating problems. The very energy needed for interstellar travel threatens to cook the spacecraft itself. Entropy also plays its silent role. Machines decay, materials weaken, electronics fail. Long-duration missions lasting centuries would require systems capable of surviving longer than entire human civilizations have existed. Even tiny defects accumulate over time. Reality itself slowly erodes every engineered structure. And perhaps the deepest reason interstellar travel feels impossible is because the universe was never meant to be small. Humans instinctively imagine reality as something built around accessibility. We assume if we can see stars, reaching them must eventually become practical. But visibility is not permission. The stars may simply be beyond us. A fish can see the moon reflected in water, but that does not mean it can swim there. Humanity may be confronting a similar truth. Intelligence does not guarantee unlimited freedom. Nature allows certain possibilities while denying others completely. The laws of physics are not emotional. They do not reward courage or ambition. A rocket engine cannot negotiate with relativity. A determined astronaut cannot persuade space-time to shrink. The universe remains indifferent. And yet, strangely, This impossibility makes the cosmos even more beautiful. Because when you look at the stars knowing how unreachable they truly are, they stop being destinations and become something greater. They become reminders of the scale of existence itself. They force humanity into humility. For centuries, people believed the oceans were impossible to cross. Later, flight seemed impossible. Then landing on the moon appeared impossible. So naturally, many assume interstellar travel is simply another challenge waiting to be solved. But history can mislead us. Some barriers fall because they are engineering problems. Others remain because they are woven into the mathematical structure of reality. That is what makes this subject so fascinating. Interstellar travel may not merely be hard. It may reveal something profound about the limits of intelligence, civilization, and matter itself. The universe may allow us to observe distant galaxies, calculate black holes, and understand the birth of stars, while simultaneously preventing us from ever physically touching most of it. And perhaps that is the strangest truth of all. Humanity lives in a universe where knowledge can travel farther than bodies ever will. And so, after everything we have explored tonight, we arrive at a strange and beautiful conclusion. The universe may be far more mysterious than our dreams ever imagined. We began with the hope that one day humanity would casually travel between stars, building civilizations across the galaxy as if the cosmos were simply waiting for us to arrive. But physics tells a different story. It tells us that space is not merely large, it is overwhelmingly, almost unimaginably vast. It tells us that time itself bends and stretches. It tells us that energy has limits, matter has limits, and perhaps even human ambition has limits. Yet there is something deeply inspiring hidden inside this realization, because the true power of science was never about making humans feel important. Science is powerful because it teaches us the truth, even when the truth is uncomfortable. It teaches us humility. It teaches us wonder. And sometimes the greatest discoveries are the ones that force us to realize how extraordinary reality already is. Think about what this means for a moment. Tiny creatures standing on a small, rocky planet, orbiting an ordinary star, somehow learned enough mathematics to understand the structure of space-time itself. We may never touch distant galaxies, but the human mind has already reached them. We may never walk beneath alien suns, but we can understand how those suns are born, how they die, and how the atoms inside our own bodies were forged within ancient stars billions of years ago. That is the real miracle. Perhaps interstellar travel is impossible, or perhaps future generations will discover physics we cannot yet imagine. But either way, the search itself matters. The curiosity matters. The courage to ask impossible questions matters. Because every time humanity looks into the night sky and wonders what lies beyond, we are doing something extraordinary. We are refusing to live only inside the boundaries of ordinary life. We are reaching beyond ourselves with imagination, with reason, and with the desire to understand existence itself. And maybe that is enough. Maybe the universe was never meant to be conquered. Maybe it was meant to be explored through thought, through discovery, and through wonder. So the next time you look up at the stars, remember this. Those distant lights are not just objects in space. They are reminders that reality is far stranger, far larger, and far more beautiful than human beings ever expected. Thank you so much for being part of this journey. I hope this speech made you think differently about space, time, and the universe we all live in. Keep asking questions. Keep being curious, because curiosity is the one force that continues pushing humanity forward, even when the universe itself seems to push back. Good luck to all of you, and never stop looking at the stars with wonder. Thank you.